G'day guys, welcome back to another episode. In this episode, I need to go through my 1926 Howard V-twin here, and I need to grind some piston rings and stuff and get this thing all finished, ready to balance the flywheel so I can assemble this thing. I'm going to go through this thing, show you a few quirky little differences between a Harley crank and a Howard crank and how they work. I'm not going to say they're in direct competition because they were built for two completely different purposes. Obviously a Harley was for transport and a Howard was for agricultural purposes. So I'm going to go through this thing, I'm going to show you how I'm going to grind the piston rings for this thing, I'm going to gap them in the bores, and then I'm going to go through a bit of the process of balancing this thing and how we're going to do that and the balance factor and all that sorts of weird things. And then we are going to hopefully put this thing together. Alright, where to start on these freaking things? So there is all sorts of quirky bits and pieces, you know, going on with this engine. Like, this thing is so far from like a Harley Davidson engine from the period. You know, when Cliff Howard, the guy who designed this, when he designed this engine, he originally used a Harley from that period as sort of the engine in his rotary hoe that he was developing. And he worked out that it wasn't, you know, fit for purpose. So he designed and built this thing specifically for, you know, stationary engines, rotary hose, all that sorts of stuff. So this engine is obviously a pocket valve engine. So the valves are underneath and not an overhead valve like later model Harley engines are overhead valve. This is an under valve. So the lifters get pushed from the lobes on the cam here. Another difference between a Harley and this Howard here, you will notice the engine runs perpendicular to the crank. So the crank runs this direction, the cam runs this direction. In all Harleys, the cams run parallel with the crank, so the cams will run this direction. So that is one of the quirky things. So the lifters push off the lobes of the cam, and then the push rods have the springs off the bottom here, and they push and open and close the valves, and that's basically how it works. But in like a flathead engine, say, all this part is one, but in a Howard you can pull all this together apart. So it comes off, this is the same as a Harley, comes off with your pocket. When I say pocket, this is what I mean. This is where the valves go into these little pockets here. And you'll see on higher compression flatheads like this, they will close all these gaps off and make the compression high by minimizing how much space is in here. So that's a head, that's pretty common, that's how most flathead Harleys are. But this is the main difference. A Howard will come apart like this. So this is the little, I don't know what they call it, but it's like a sandwich plate that has your valve seats and everything in it. So you know, in like a Harley, you would pull this off in one piece. I'm not sure if you've seen a flathead, but you'd pull this off in one piece. This would be a flathead. This would all be one piece. So I suppose the pros of doing it like this, if you were to damage your valve seat, or you know, maybe you damaged your exhaust port or something, you can just replace this sandwich plate here. So you can throw that away and put a new one on. Where with a Harley, you can't do that. This is all one piece, and you'd throw away the bore as well. So that's a pretty cool little feature of these. The only downside to this is you have to run a gasket both sides. So you've got twice the amount of gaskets. So you've got one on the bottom, then you put that on, and then you've got another one on top for the head. So a little bit annoying, but I think it's going to be pretty cool. So let's put these to the side. As I said, I'm basically doing this video because I had to do a few things before I balance this engine. As I said in the intro, I need to have all the weights calculated and then work out the balance factor before I can balance this crank. So in order to do that, I need to have all the piston rings ground to the right size and all that. So at the moment I am making one engine out of a few. Like this engine back here, this is actually a rotary hoe engine. I probably should have showed you that before I took this apart differences between a rotary hoe engine and a stationary engine. So stationary engines are just a little engine that'll sit beside a dam, pump water, you know, it might sit beside something that it needs to run a generator and then it's powered. So these are a bit tricky to go on sometimes, there it is. So the differences between them is obviously they have some engine numbers that are a bit different. The engine numbers on a Howard are right here. So a stationary engine always starts with an M. So we've got an M533. So as you can tell, only a 4-digit VIN. So this is going to be fun to register. So as I said, the VIN's different between a rotary hoe and a stationary, and also you can look at the spark plug location. See how the spark plug comes straight up out of this head, and in this head it's on an angle. That's how you tell the difference. On the angle is rotary hoe, straight up is your stationary engine. So basically I'm gonna kick these castings to the side because they're pretty standard little things. There's nothing too quirky going on with them. They are cast iron though, so they are super heavy. So obviously, only the really, really early Harleys are cast iron cases. So they are super heavy, but makes them super durable as well. Like this thing is 1926, right? And there's freaking no broken tabs, no chips, no nothing on this thing. Like a Harley of the same year would be absolutely destroyed in the cases. Let's go through the crank. So we'll go through the crankshaft here. I'll show you the differences. I've got a Harley one over here. Oh shit. This is a crank out of an Evo that I'm putting together at the moment, but they're all basically the same crap. So first off, you can see the size difference. Although these are exactly the same CC, this is a 1340 and so is the Howard. You can see their size difference in the things. So let's start with a Howard and I'll just show you the differences between the Harley and the Howard. So for starters, the Howard on the outsides of this Howard crank, it has a roller bearing instead of the Harley here has these these roller style. So these roller style bearings are much better than a ball bearing for load impact. So where this engine's going to have a lot of load impact because it's always firing down into itself. So the bearings must be good for different purposes. As I said, this guy's a roller bearing, a ball bearing, sorry, and this guy is a roller. So it has the rollers instead of the internal balls like this guy's got. The advantage of this internal ball guy is it has axial load both directions. So you'll hear me say axial load a few times. So axial load is the load that the bearing can withstand on a side. Usually a bearing, all the loads straight up and down. But on an axial load bearing, it can take load side to side as well. Where this style bearing, which is on a Harley, can only take load in this direction, can't take sidewards load. So the advantage of doing that is the Howard engine can use these bearings and then just lock them into the case, and then it doesn't have to worry about the crank doing this inside the cases. Where a Harley, for instance, has rollers on one side, and then on the other side, it has a taper bearing. So with the taper bearing, it'll have two races each side in the case. So one bearing will be that direction, and the other bearing will be the opposite. And then you've got this guy on the outside, which you tighten up with your crank nut, and that puts pressure on these bearings, and that stops the crankshaft from floating back and forth. Where a Howard doesn't have to worry about that because it has ball bearings on both sides that can handle the axial load. So that's one difference between the two. The other major difference is the Conrods in this thing. So these are the rods for the Howard. Now I had to do some pretty hefty modifications to make these rods fit just because you can't buy these bearings anymore. So these are later model metric bearings that I have retrofit into these Howard Conrods here. So I have the original bearings here, I can show you. So I tried to buy these bearings, right? Went to every single, bearing shop that I had within 100 Ks. Everyone told me you're dreaming trying to find these bearings. So just like the ball bearings that have axial load, these are a roller bearing that can take axial load. So the way they do that is they're a few part. So you can see you've got your inner race, and then you've got your outer race, and then you've got ball bearings that will fill the inside through this side, and then you've got this cap that will keep the bearings in there. So as I said, every bearing shop that I went to said I was insane trying to find this, because this is imperial size, just a weird size, and you can easily buy this bearing in a ball bearing, but I don't think it'll cop the load from the compression from the combustion. So I had to retrofit metric bearings. Now funny, they had, for this original style bearing, they didn't have stock, but they had a price. So they wanted 700 Australian dollars for each of these bearings. So luckily they didn't have a listing, because I probably would have bought them, but no, I wouldn't have. I'm a tight ass. So what I did was I had to take metric bearings and make them work. So these metric bearings are a smaller OD and a bigger ID. So that means I can make adapters to make them suit these rods. Now, I'm not sure if you'll be able to see how small this adapter is, but I've got to pull these apart. So let's pull these apart. So as I said, these are double axial load bearings as well. So just like the other bearing, I have an inner like this, and then I can push the outer out like that. So the ball bearings are shown like that. So by having these two bits, I can crush the sides and still have the, the rod work like that. So if you have a look in here, you can just see a stainless ring around the outside there, just really lightly. So that is the shim that I had to make the OD of this bearing fit the ID of the rod. So that is a stainless steel shim. I think it was maybe it was 12 thou a side. So it's super, super small shim. So the bearing's pressed in there, and basically the shim is so small, if you pressed it in there, it wouldn't do anything. But because I've pressed the bearing in with it, it holds in there. So the other thing you'll notice is I have a gap this side on the inside, and on the outside is flush. Now the reason it's like that is because of how this engine oils. So the way this engine oils, this engine is only splash fed as well. So everything else in this engine is splash fed, but these main bearings in the rods, they are pressure fed by the pump. So the way that works is pretty cool. So this is this side of the case. So this is how the crankshaft would go in the cases here. So it has a hole up the middle of this pinion shaft here. So that hole goes through, and then it has drilled holes in the crankshaft here, and that'll go up into the pinion shaft, which holds the rods on, and the oil will go through the rods and then spray out into them. So as I said, I had to retrofit these bearings on the OD and the ID. So on the ID, I had to make this guy. So this is obviously one side of the bearing will go in here like that, and then the ID presses onto the pinion shaft in the crankshaft. So this presses in, and you can see it has this hole in it. I need to do a little bit of machining on this yet, but it has a hole in there, and that is to line up with the oil hole in the crankshaft, so the oil will go through and then spray out. Another cool little feature of these engines, so that lives in there like that, and then the other guy lives on there like that. But if you were to just have that on there like that, the oil would just spray out in between the rods and not go through the bearing. So what they do to stop that, they have another little shim here. So what they do to stop that, they have this stainless ring. Now I had to make this because obviously I retrofit all these, but on the original bearings, this is how it worked. This is a stainless ring that lives in here like that. So that lives between the rods. So it goes together like this and lives between the rods. And the idea of that ring is so the oil can't go through the center of the rods between here. It has to go through the bearing. So that is super cool. So that means that the oil is going in the center through this hole, and then it has to go through the bearings. It's forced out the side here through the bearings. And as I said, this whole engine is splash fed. The whole cam system splash fed. That is the only oil pressure area in the engine. You see how the Howard are side-by-side rods. So they are side by side of each other. Where with a Harley, the rods are knife and fork. And when we say knife and fork, that's what we mean. They come apart like that. One goes inside the other. So that is a big difference between a Harley and a Howard. And you can see where all the roller bearings sit in there. They're the races for the roller bearings. So that's completely different to the old Howard here. So those are the rods. I think I've covered that pretty well. They are super cool. I might as well go through this crankshaft now and show you the oil ports that I was just talking about. So as we said, this thing has a ball bearing each side, and that is so you don't have to worry about the axial load. So ball bearing that side, ball bearing this side, a bit larger on the drive side because there's obviously a bit more pressure there. So this is the pinion shaft. So this is the shaft that holds the two counterweights together like that. So this shaft is keyed as well. So the reason it's keyed is because on the other side, this is your oil passage. So in the flywheel, like I said, so oil goes in here, and then I'm not sure if you can see it. See that hole just here? That hole is where the oil goes through and then lines up with this hole up in there, and then that hole will line up with the hole in the center of my Conrods here. I'll pull this apart. So that hole on this guy lines up with this hole here. So the oil goes all the way through to the center of the engine. So that is how we keep this thing alive. And something cool, a difference between a Howard, how the Howard bearing works and how the Harley works is completely different. So on the Howard, all you do is, because these bearings have axial load in both directions, you lock this up tight on the races of the bearings. So usually on a Harley here, it's locked up on two tapers so that the rods don't have weight on the side of them because they can't handle weight on the side. So they have a little washer here, a little brass washer here, and that is the thrust washer. So these things can ride up and back on it. So that's another cool little feature between the Howard and a Harley. That's pretty tricky to get right on a Harley, but on a Howard you don't have to worry about it because you're just locking the races up together. Now a Harley, as I said, is obviously more of a transport engine. It revs a lot more as well. So there's different bearing engineering and stuff in a Harley. Mind you, that crankshaft is from an early Evo, so that's from 84-ish, where this is from the 20s. So huge difference in years there. But basically that is the crankshaft here. That's all pretty normal. The pinion drive shaft, that's all pretty normal. So that is basically the crankshaft gone through. As I said, I still got to go through this and balance it. So if you want to learn more about balancing, I'm no expert on it. As I said, I did that frame for my buddy John Parker. He's really good at balancing engines. So I sort of have a brief idea of how it works. I want him to hands-on show me because it's, you know, you learn a lot more from being shown in person than reading a bunch of, 200 pages of literature about it. So basically the way balancing works is you have a rotating mass and reciprocating mass. So your reciprocating mass is your mass that moves up and down, and your rotating mass is the one that rotates. So you're probably wondering, a Conrod does both those things. It rotates and it goes up and down. So the way you fight that is you measure half of the rod. So you measure one half of the rod, so the front half is your reciprocating because it goes up and down, and the bottom half is your rotating. And once you work all that out, obviously your pistons are reciprocating, so you work all that out, and then you measure it all by weighing it. So that's really crucial. You have to have like a really accurate scale for that. So you weigh it all, and then you divide it by a balance factor. And your balance factor is determined on your V. So a Harley V is 45 degrees, my Howard V is 50 degrees, but you just do them on the same balance factor because they're close enough. But so basically, to work out my rotating and reciprocating, I need to get all my pistons and rings and stuff ground. So these are the pistons for this engine. These are, I'm not sure if you can hear the difference, cast iron. So these are spun cast, so really, really thin, and they are pretty light actually. And like these engines would cop heaps of heat because obviously they're a stationary engine. They're not in a vehicle traveling down the road. So they do have like their own fan that blows air into them, but these things would see some crazy heat. So by making these all light means they don't absorb much heat and they don't expand much. So I'm going to go through, I've got some rings for this thing here. These have come out of one of my spare engines that I've got. Usually with your rings, you've got a compression, you've got like two compression, and then you've got a wiper ring. So these compressions are super thick, and the wiper's a pretty weird wiper. Usually they're like a squiggly thing that goes around, like 3-piece, where these are just a single wiper style. So pretty cool little rings there. So we're going to go through now. I'm going to go through and grind these. We're going to have a look in our Harley book, work out what gaps they need. You can have a look in there. There's actually a lot of stuff online about what gaps your engine's rings should be. So in an engine, your piston ring obviously sits in your bore, right? And the smaller this gap is, the less compression will go past it, so the more economical it'll be. But when an engine's cold to when it's hot, this is expanding and contracting. So when these engines get hot, if you don't have enough ring gap, this ring will crash into itself. And when the ring crashes into itself, it does this. And it pops the top of the piston off or breaks your lands or whatever. So you're on both sides of this. You want to have as little gap as possible so you keep as much compression in, but you want to have enough so this thing doesn't crash into itself and explode your piston ring. So online they talk about different applications. Like if you've got a boosted application, if you've got a nitrous application, obviously we're not doing any of that with this old crap, but they tell you all the different ring gaps you can be. There's even a formula that tells you like the circumference, so how much material mass you've got and how much that will expand. So it's easy with Harley stuff. You can just go into the book, whatever year you got, in the back it'll tell you what gaps they should be. Sometimes your compression ring is different than your second ring and your oil ring, but it's best just to go and have a look, and that's exactly what I'm going to do. Even though this thing's not a Harley, it's basically the same bore size, same stroke, everything. It's not going to make a freaking difference. So I'm going to get started on this thing. I'm going to set my bores up. I've already honed them. There's a few scratches in them, but there's no way I'm going to find new ones or bother, boring them out and putting sleeves in them. So I'm going to go through, set that up, and then we'll go through and start grinding some of these rings. Alright, so I have all my shit set up here. I have my rear piston, my front piston, rear jug, front jug. I have some measuring gear here because I just want to go through a few little bits and pieces. I'm not too worried about this thing because it is as old as it is, and the tolerances are probably huge because this is a stationary engine that would get super hot. So I've just got my trusty Harley Climber manual here. This thing's seen some shit, but this is just my workshop one. I've got a nice one in the house. If you go into your chapter 4, this is your piston inspection. So you just want to go through, I've already cleaned these things up. You just go through all your little ribs here, all your little landings, clean up that, clean up any, there was heaps of carbon build up in these pistons just because of what they were, but I cleaned all that up. The reason I got all the carbon out of these things is because when we weigh it, they will be heavier. So I had to get these things spotless clean so they weigh correctly. So basically what I've got here is just talking to you about measuring your pistons, doing all that crap. The directions your rings go. So this will be important for later. We're gonna get into this. So your pistons rings are just sort of facing all away from each other because you don't want them to line up, because that's when it will, leak heaps of compression past it. So it talks about a lot of stuff here and then talks about this here, which is what I really want to get to. This is your piston ring end clearance. So if we go to the back of this book, into the table, the back of the chapter, sorry, into the table, it's got all the different things here. So it's got your intake, your inner, your rocker arm, end clearance, blah, blah, blah. We are looking for piston. Piston, and this has all your clearances. So right here, it's got piston clearance. So that's something I want to have a quick little look at just because that's pretty important for this. So piston clearance is the clearance of the piston in the bore. So you want this thing pretty clean. So let's just clean this thing up. So it is clean. You want to get all the crap off this just so you don't scratch the bore. Like I said, I've already honed these. So your piston clearance is the clearance between the piston and the bore. So there has to be a bit of clearance there because this piston expands when it gets hot, especially at the top where there is lots of material, because the more material, the more it'll expand. Usually the top of the piston is smaller than the skirt because there's different amounts of material there. So as you can see, that thing is pretty sloppy in there, but we just want to have a bit of a look. So I've just got my little telescopic gauge here. Now the other thing you want to look at this thing in a few directions to make sure that your bore is round. I've already done this, but I just do it a dodgy little way. So we just want to set this thing up. So you just like that, set, you just want to go around it, make sure it feels all right. Yeah, so this thing is tight all the way around, has tight spots, which tells me that this thing is fairly round. So what we're going to do now, we're going to set this up. I have a little book, a little pad here, just because I want to be able to write some stuff on this. Now I forgot a fucking pen. All right, so what we want to do on this thing, let's just put a line down the center here. So rear piston, front piston. Oh, piston, whatever. Rear cylinder, front cylinder. So what we're going to do, we want to measure the bore on our rear and front jugs. So we're going to go bore here. So that's going to tell us the bore. So let's go through, we'll do this again. So with these things, they're pretty cool. You just close them, and then this top bit, if you undo it, it does that. So what you do, you undo them above parallel and then tighten it, and then you just give it a nice little feel like that over parallel, and then that is perfectly the right size. Then we get our mic here. I've already given this a bit of a measure so I know what it is. So this, I'm going to measure this in metric because I'm Australian and not US. So this thing is, what do we got there? 89.95. So let's have a look at front cylinder now. Hopefully they're pretty similar. I haven't measured them both yet. 89. Fucking pretty well bang on. So they're both 89.95. Just under 90. 9.95. So now what we want to do, we want to go through and measure our piston. Now I'm going to do this in a few spots because usually it is a little bit different. So let's measure here. So that is 8.5. A bit under 8.5. measure here. That's pretty close. A little bit under. So that is like 89.80. So 89, oh wait, that's wrong. What's this? No, this is rear cylinder. 89.80. So that's that guy. And then let's do this guy. I'll do a little conversion here in a second for you Americans so we can work it out in thousandths, because you guys are probably lost. So this is pretty well the same. Pistons are the same. So 89.80. Give me a sec. I'll do a little conversion on my phone for you guys. So let's do it. 89.95 minus 89.8 equals 0.15. So in our little book, it'll tell us in metric as well, in millimeters. So this thing is probably, twice what it should be, which I'm not worried about because, like I said, this is a stationary engine. They're probably engineered to be able to get super hot and not hurt themselves. So what's this? 0.15, let's divide that by 40. 0.15 divided by 40. So 6 thousandths we got. So yeah, it's about double what it should be, which I'm not worried about because, like I said, I lost my page. Here it is. Like I said, this thing is a stationary engine, not worried about it. It'll be fine. So next thing we want to look at is so we've done piston clearance, we want to do ring fit. So piston ring end gap, they say 10 thou to 20 thou. So 20 thou is probably closer to what I want to be on this engine, just because, like I said, it is designed to get super hot. So usually when I do a Harley, I shoot for that 12 thou, but I'm going to shoot for probably a bit more. I'll probably go that 20 thou just because it is what it is. And I want this thing to live. So we've done that. Let's go and do our piston rings. So we want end gap 20 thou. So same for this side. So we got all that together. I'm going to get my little grinding rig together here. I'm going to find myself my feeler gauges, and then we're going to grind some rings. Alright, so what we got going on here, I have my trusty little ring grinding tool here. Usually you've just got a little handle on this thing, but I freaking motorized mine just to make this a bit quicker. So basically what we're doing here, we're just setting out our rings here. So obviously there's 3 rings here. I've got 2 compression. I'm pretty sure a lot of Harleys, they have a compression, then you have a middle ring, and then you have your wiper. This wiper's one piece as well, so I've just got 2 compression, 1 wiper here. I'm going to go through them, gap them all the same. We're going to shoot for that 20 thou in this engine. Like I said, when I do a Harley, I do like 12. So I just want to go a bit more in this engine. I want to give this engine a bit more clearance just because, this thing is super old and loves a bit of heat in it. So basically what you do to check your rings, you just put them in your bore, obviously. Firstly, you want to make sure there's plenty of spring to them. When the engine's had a lot of heat, this spring will go away. So the spring is what holds the compression in your engine. The spring is pushing the ring into your bore. So basically we want to just stick this thing in here, and mine overlap. So I've got heaps to come out of these things. So basically all we do, we just come over here to this guy. You want it running towards the bottom of the table of the machine like this. Put her in there. Make sure the ring's fairly square. Takes off quite a bit of material at a time, so just go easy on it. Sometimes it leaves like a little burr on it, so I like to go through and just give this a quick little file where the burr is, just so you don't scratch your bore. So what are we working with? All right, so I just have a gap here. So what you do, you put your ring in just like that, and then you get your piston, and you just want to push the head of the piston in just over like ½ an inch or an inch or something, just so it gets down in the bore, just like that. So then that little gap you see there, get your feeler gauge. So I just got a 20 thou feeler gauge, and you put him in there like that. So obviously it doesn't go in there, so we need to go a little bit more yet. So take him back out, come back around to the trusty little steed here. Like I said, this thing takes quite a bit of material, so just go easy. Let's give that a look. Have a little file just so I don't scratch the bores. Jam that guy in there like that. Get our piston again. I just go to the end of the rings just so the end of the ring grooves on that, so I know it's right. Have a look again. Oh, it's just tight. So we're getting pretty close there. So let's do it again. I reckon this is going to be it. Get this burr off. There's plenty of spring to these rings too, which is nice. Means they are ready to roll. That looks better. So you're starting to really see that ring gap now. That's it. So my feeler gauge goes in there nicely, and that is freaking done. So I'm going to go through and do this on every single ring now, because you've seen one, now you've seen them all. So I'm going to go through and do all the rings, and then we're going to come back and have a look at this thing. Righto, so I have done rings on both cylinders now. So basically now that I have these rings all set up now, I can start to weigh this engine and work everything out. Alright, so the last thing I need to do on this engine before I can balance it is I need to finish the machining on this little adapter that I had to make. This was the adapter that goes on this pinion shaft here. So this is the one that has the oil hole through it. Now this is a press-on fit, so I don't want to push this thing on because I probably won't get it off. So the only problem is this hole is only in one spot, right? So if for some reason this bush that I made spins, if it spins, that means the hole no longer lines up. So what I'm going to do, just in case this thing spins, it's a press-on fit like I said, but if something goes on in there and it spins, I don't want to have to take it apart because it's blown the bottom end up. So what I'm going to do, I'm going to come in here with my boring bar and I'm going to cut a groove around the hole where this oil comes through. So if I cut a groove, what that means is this thing can spin on here and it doesn't matter. The oil will still find its way out this hole and into my big ends. So I'm going to put this in the lathe, I'm going to machine that thing, and then I'm going to give this a little bit of a harden, I think. How I'm going to do that, I'm going to heat this thing up super hot, and then I'm going to quench it in oil. Maybe a couple of times I'm going to take a file to the side of this so I can see when it's getting a bit harder, and then I know when it's nice and hard, and then this whole bottom end is ready to weigh up and then balance. Alright, so we are over here at the trusty little lathe here. As I said, all I need to do to this, I just need to cut a little groove in here in exactly the same spot as the hole. So all I'm going to do is just chuck this in here. Just got a simple little boring bar in here. And all I'm going to do, I'm just going to make sure the thing's height first, so the height's right. I'm just going to send that in there and line it up with the hole. So because I can see the hole from the outside, it's pretty easy. So all we're going to do is give this a spin and make a little groove. So a little groove in there. That looks pretty good. Might just go a little bit more just to make sure she does what we want. Sweet. So we have a little groove in there. I'm not sure if you guys can see it, but now I have a little groove through the whole thing. So if this thing were to spin on the shaft, which it shouldn't, but if it did, the oil would still get out this hole because we have a groove around the whole thing now. So what I want to do now, I want to give this thing a bit of a harden. So I'm going to set up my little propane torch and we will burn this thing, get it super hot, and then dump it in some oil. All right, so I have my little setup here. Whenever you're heating up a bit of steel, put it on a brick or something like that, because if you were to put this on a bit of steel or whatever, you're going to be heating up the massive bit of steel underneath it. Or if you've got a flat plate, all the heat that you're putting into the plate will transfer into whatever metal bench you've got. So if you use a bit of brick like this, then the heat doesn't just transfer into the brick. It's much better. You will focus the heat on your steel. So what I was talking about before, if you want to sort of test how hard something is, getting a file and hitting the side of it is a good indication of how hard it is. If it removes material easily, you know it's soft. If it just runs straight off it, you know that it's super hard. So I just take like a bit of like this, so I know the hardness we're working with, and then I'll check it again after we heat and quench it. So when I say quench, I mean cooling it down in something quickly. So you can do it in water, but the best way to do it is in oil. Because when you quench this in the oil, it removes stuff from the oil and then soaks it into your metal and makes it harder. So usually like a diesel oil that's done like 200,000, that's full of carbon, is the best for quenching pieces in. And don't be an idiot and have something plastic with oil in it and then drop this in it, because this is just going to burn straight through the bottom. Get your finest beer can and quench it in that. I just put some of the oil out of this pan head that I just did in that. So I'm going to drop it in that when we're done and quench it. But for the time being, let's heat this thing up and get it red hot, and then we'll dunk it in here. Alright, so this thing's nice and hot now. Let's dunk it in here and see what happens. Woo! It's a full witch cauldron. So this oil is going to be super hot. Probably should have done it in a bigger volume, but this is going to do the job. So I'm going to cool this thing completely down now with some water, and then we're going to test how hard it is. And if it's not very hard, we'll just keep repeating the process until it's as hard as we want it to be. All right, so this is the little bush after we've just quenched it. Now you can even hear the difference. This thing sounds harder. Now, I'm not sure if you'll be able to hear it from before, but listen to the file on this now. See how it's no longer cutting it? It has a really low-pitched sound. That means it's not cutting, it's getting really hard. So I think I'm gonna quench this one more time and then it'll be done. So let's repeat and do it all again. All right, so now this thing has been quenched twice. You can really hear the note difference when you run a file over it. Just doesn't take any material off now, and that tells you this thing is plenty hard. So this thing being done, the rings being done, this thing is ready to mark up and balance now. So that's pretty well it for this episode. Hopefully in the next one, I am assembling this thing. So if there's anything else you want to know about this thing, leave a comment. What do you think? Do you like more? Do you like this Howard project more, or you like that twin front-headed Evo project more? Let me know, and we'll see you on the next one.